Okay, till the last class we have discussed about the paged memory management, segmented memory management, and paged segmentation or segmented paging. So in all those cases we have seen that the main memory is divided into a number of partitions. In case of paged memory management, the partition size is same, every partition is of the same size. In case of segmented memory management, the partitions will be created depending upon the module size or the segment size that you want to put in the main memory. Whereas in case of paged segmented memory management, we have seen that every segment will be divided into a number of pages, and the main memory, as in case of paged memory management, is divided into partitions of same size or frames, and different pages of different segments will be loaded in different frames in the main memory. So in case of paged segmentation, every segment will have a page map table, as in case of paged memory management, that every job will have a page map table. Today we'll discuss about another memory management technique, which is called demand paging. Or this is also known as virtual memory management. So either demand paging or virtual memory management. So in case of this demand paging or virtual memory management, as the name implies, that this is a sort of paging technique. That means the main memory will be divided into a number of partitions of equal size or a number of frames. Now, as we have just mentioned, that when you execute a job, in that case it is not necessary that all the pages of the job should reside in the main memory at a time, because the instructions are executed by the CPU one at a time. The CPU will not execute more than one instructions at a time. Okay. So it is the instruction which is executed by the CPU. If you put only that page containing that instruction in the main memory, in that case execution of the program will continue. Okay. So in case of demand paging, the concept is, initially let us put only one page in the main memory, because the limitation in case of paged memory management or in case of segmented memory management is that even if the pages are not available contiguously, the pages those are available are distributed in the main memory space, but even then the total number of frames in the main memory which should be available should be equal to the number of pages of the job that is to be executed. Otherwise you cannot execute the job. So that again puts the limitation that the minimum number of frames which should be available for a job to be executed. So even that limitation is avoided in case of demand paging. So here what we are saying is, even if we can load only one page of the job in the main memory, then also the job can be executed. And the reason is very simple, that for execution of a job, it is not necessary that entire logical space of the job to be loaded in the main memory. Okay. So here again, the main memory is divided into a number of frames of equal size. So if I say that this is the main memory, which will be divided into a number of frames of equal size, the logical space of the job will also be divided into a number of pages, and page size and frame size will obviously be the same. So this is the logical address space. And this is the physical memory. Then as we have seen that in case of demand paging, for every job we have to have a page map table or PMT, So this page map table maps the page numbers into frame numbers in the main memory. So every entry in this page map table will point to a particular entry in the physical memory. Okay, and the page map table will be addressed by the address generated by the CPU. So CPU generates an address which is in the form of two components. One is the page number, other one is the offset within the page. Using the page number, you address a particular entry in the page map table. From the page map table, you get the frame number where this page is loaded. Using that frame number and the offset within the page, you come to a particular address in the physical memory and access that particular location in the physical memory, either for reading or for writing. Okay. So in case of page memory management, we have seen that the size of the page map table should be such that it should be able to accommodate all the pages of the logical space of the task. In case of demand paging, since we are saying that I need not put all the pages of the logical space in the physical memory, so in the page map table, I will have entries corresponding to those pages which are loaded in the main memory. There may be other entries in the page map table as well, and we have seen that those entries may be either a valid or invalid bit, and that gives you protection of a particular job against other jobs. For demand paging, since we are not putting all the pages in the main memory, so there will obviously be some pages of the logical space which will reside on the secondary storage. Okay, so in addition to having a pointer to the physical memory, I also have to have some pointers which points to the addresses in the secondary storage where the page is contained. So along with page map table, we will have another table for every job which we call as file map table, or FMT. Okay. So this file map table will give you the address of the secondary storage which contains different pages of the logical address space. So I have this secondary storage or disk, and the entries in the file map table points to different blocks in the secondary storage which contains that particular page. Now what is this block? That will come later on. So idea will now be like this, that whenever the CPU wants to access any memory location, the CPU generates the page number. Following this page number, you come to the page map table. In the page map table, there will be a bit which is called an interrupt bit. Okay. So if the interrupt bit is 0, that means the page exists in the physical memory. So you simply convert this logical address space into physical address, this logical address into physical address, and access that particular location in the main memory. If the page is not loaded in the main memory, in that case the interrupt bit will be set to 1. Okay. So if the interrupt bit is set to 1, then there will be an interrupt which is called a page fault interrupt. That means the CPU is trying to access a page which is not present in the main memory. So there is a page fault interrupt. Following the page fault interrupt, now the operating system has to check this file map table. From the file map table, it has to get the address of the page on the secondary storage. Okay. Then from the secondary storage, this page has to be loaded into a frame in the main memory which is free. Now it may so happen that none of the frames in the physical memory is free where this new page is to be loaded. So in that case, you have to replace one of the pages in the physical memory to make room for this new page. So then again we have to decide that out of so many pages which are there in the main memory, which page to replace. So that leads to different page replacement algorithms. Okay. So if I put this entire process in the form of a flow diagram, the flow diagram will appear something like this. First, you start processing an instruction. So while processing the instruction, the CPU will generate an address, and in general, and maybe this address will be the address of the data that is to be read, or address of the memory location where a data has to be written. Okay. So while processing this instruction, the CPU will generate address, from this address page number will be generated, then with the help of this page number you have to check the page map table or PMT to find out whether the page is available in the main memory or not. So the check that has to be made is page in main memory. Okay. So if the page is available in the main memory, then you don't have any problem. You can simply execute the instruction and go to the next instruction. Okay. So if the page is available in the main memory, what you have to do is fetch the data and compute the instruction. Then after this instruction is computed, then the CPU advances to the next instruction. And the process continues. Now, in case the page is not available in the main memory, then you have the problem when a page fault interrupt is generated. Okay. So this is the condition when you generate a page fault interrupt. So here we put as page fault interrupt. When this interrupt has to be processed. So let us see that what are the operations that you have to perform when a page fault interrupt occurs. Let us go to the next page. So whenever you have a page fault interrupt, the first thing you have to check is, because there is a page fault interrupt, that means page does not exist in the main memory, you have to bring it from the secondary storage into the main memory. So the first check that you have to make is whether there is any free block in the main memory or not. Okay. So first you check, is there a free block? If there is no free block, then as I said, that one of the pages which are there in the main memory has to be replaced. Okay. So the first operation that you have to do is, in case there is no free block, that you have to select a page for replacement. So once you select a page for replacement, in that case you check the page map table of the job from which the page has been selected, because now the page map table of that job has to be modified. Okay. Earlier this page was present in the main memory, now we are removing it from the main memory. That means the corresponding interrupt bit in the page map table has to be set. So next operation that you have to do is adjust page map table. Okay. So after adjustment of the page map table, I can have two different situations. That is the page that I am going to replace. Maybe this page was modified while it was in the main memory. Initially this page was brought from the secondary storage following some such page fault interrupt. Okay. Then while this page is in the main memory, in that case the page has been modified. So if the page is modified, in that case I have to write this page back onto the secondary storage. The other situation may be that though we are replacing the page, but while in the main memory the page was not modified. So if the page was not modified, you already have a copy of this page on the secondary storage. So I need not write back this page onto the secondary storage. Okay. So before overwriting this frame with the new page, I have to make a check that whether the page is modified or not. So was I have to check this. So if the page is modified, in that case I have to write this page back onto the secondary storage. Okay. If it was not modified, in that case I don't have to do anything. I can simply overwrite the frame with the new page. Okay. So with this, what I am doing is I am generating a frame which will be used for loading the new page. Okay. So after doing this, the next operation that I have to do is get disk address of the new page from file map table. Okay. So once you have the disk address, now you can read in the page. Once the page is read in, the corresponding page map table has to be adjusted. And after that, you have to restart the interrupted instruction. And when you restart the interrupted instruction, that means you go to the initial step of instruction execution, that is this one. Okay. So let us see that what is the total sequence that you have to follow. You start processing an instruction. So when you start processing an instruction, it is assumed that the address of the instruction was coming from the program counter or from the instruction pointer. So while the instruction is processed, the instruction while execution will access some memory location. There may be some instructions which are register reference instructions for which a memory access is not needed, and obviously in such cases you won't have the page fault because you are not going to access any page from the main memory. But assuming that you have a memory access, the address of the memory location will be generated. From that you compute the page number and correspondingly offset within the page. But offset within the page is not important at this moment because what we are checking is whether this page is available in the main memory or not. So you compute the page number. With this page number you come to the page map table to see whether the page is available in the main memory or not. If the page is available in the main memory, then you have very simple operation. You simply fetch the data for which the address was generated, compute the instruction, advance to the next instruction and continue. But in case the page was not available in the main memory, that means the corresponding entry, the entry corresponding to this page number in the page map table had interrupt bit set to 1. Okay. So in that case there will be a page fault interrupt. Following page fault interrupt, you have to process this page fault interrupt. So since the page fault interrupt happens due to the fact that the page is not available in the main memory, so I have to bring the required page into the main memory. So before bringing the page into the main memory, I have to see whether there is any available frame in the main memory or not. So you check if there is any free block. If there is no free block, in that case I have to select a page from one of the frames which will be replaced to make room for the new page that has to be brought in. So I select a page for replacement. And obviously, since I replace this page, the corresponding page map table has to be adjusted. So you adjust the page map table. And after that, before overwriting the frame that has been selected, I have to check whether this page which is being replaced has to be saved in the disk or not. So if the page was modified while this was in the main memory, in that case, there is no copy of this onto the secondary storage. So I have to write back this page onto the secondary storage. Okay. So you have to write back this page on the disk. If the page was not modified, then a copy of this is already available on the secondary storage. So I need not write it back. So I simply come here. So in this path, what I have done is I have found out a frame. I have made a frame free where the new page is to be loaded. Okay. So you come here, then you get the disk address of the new page from the FMT. That means this is the page which is to be brought from the secondary storage in the main memory. So from FMT you get the disk address. Once you have the disk address, you can read in the page. Once you read in the page, the corresponding page map table now has to be modified because earlier the entry in the page map table had interrupt bit set to 1. Now the interrupt bit has to be reset, and not only that, the frame number where this page is loaded also has to be inserted in the page map table. Okay. So all these adjustments are to be made in the page map table. And when all these things have been done, then you are ready to restart the instruction that has been interrupted. So you restart the interrupted instruction, and restart of interrupted instruction means you start processing the instruction. So you go back to the initial stage. Okay. So now, as we said, that when you replace a page, there can be different kinds of page replacement techniques. Okay. The simplest page replacement technique that can be used is called FIFO page replacement, or first in, first out type of page replacement. Now what is this first in, first out type of page replacement? That is, out of the pages which are then there in the main memory, the page which was brought first has to be replaced. Okay. However, there may be a problem that the page that you have replaced just now, maybe that is the page which will be referred next. And because you have removed this page from the main memory, so next time this page is going to be referred, there will again be a page fault interrupt. Now obviously by this time it should be clear that whenever you have a page fault interrupt, that slows down the process or reduces the system efficiency, because every page fault interrupt means there is an IO operation. That is, you have to read a page from the secondary storage. Until that reading operation is complete, the CPU cannot proceed with execution of that instruction. And maybe there will also be a swap out operation for writing the page from the main memory into secondary storage. So the page fault interrupt is something which is not desirable. Now if I have a situation like this, that the page which is replaced, that is the page which is going to be referred next, in that case it is bound to reduce the system efficiency. However, this is the simplest approach, that is first in first out. Simply the page which was brought in the main memory first, that is the one which is to be replaced. The second kind of page replacement technique is optimal page replacement technique. Optimal means I cannot have anything better than this. Here what you try to do is, you replace that page which will not be referred for maximum duration in future. Okay. So if I replace a page which will not be referred in near future, in that case I'll have minimum amount of page fault interrupt, because I have removed a page which is not going to be referred next. Okay. So though optimal is the best type of page replacement technique, but it is difficult to implement. We will see the relative performance of each of them. Now, an approximation to optimal page replacement technique is what is called an LRU page replacement technique, or least recently used page replacement technique. Okay, so we'll discuss these three kinds of page replacement techniques with the help of a sequence of page numbers, which are, of course, that is a hypothetical example, which are generated by the CPU. Okay. So suppose the CPU generates a sequence of page numbers, something like this. So 7, 0, 1, 2, 0, 3, 0, 4, 2, 3, 0, 3, 2, 1, 2, 0, 1, 7, 0, 1, maybe something like this. So what it says is, these are the page numbers which are referred by some program, by some user process in this sequence. Okay. And we'll see the performance of different page replacement techniques with the help of these three replacement techniques, first in, first out, optimal and LRU. Okay. And we assume that in the system we have, or in the main memory, we have 3 frames available for accommodating these pages. And all these three frames are initially free. Okay. So let us start with the first one, that is FIFO technique, or first in, first out technique. Okay. Now when you go for this first in, first out technique, you see that the first page which has been referred is page number 7. Right? And initially, as I said, that we have 3 frames which are free and to be used for accommodating all these pages. Initially, there is no page in the frames. Page number 7 is referred, so obviously there will be a page fault interrupt. Okay. You have available number of frames, so no replacement is required. You simply put this page number 7 into one of the available frames. Next time, page number 0 is referred. Again, page number 0 is not available in the main memory, but I have 2 more free frames, so again no page replacement will be needed. I simply put this page number 0 also in the main memory. So I have already page number 7. The next page 0 is also put in the main memory. The next page that is referred is page number 1. Again, page number 1 is not there in the main memory, so there will be a page fault interrupt. Following this page fault interrupt, page number 1 will also be put in the main memory. The next page that is referred is page number 2. Now you find that page number 2 is not there in the main memory, so there will be a page fault interrupt, and at the same time there is no memory, no free frame available to accommodate this page number 2. So I have to go for page replacement. In case of FIFO, as I said, that out of these pages which are there in the main memory, the page which was brought first will be replaced. So out of these pages, the page which was brought first is page number 7. So we simply replace page number 7 by page number 2. The other pages will remain as it is. Okay. Next page that is referred is page number 0, which is in the main memory, so there will not be any page fault interrupt. Next page that is referred is page number 3. Okay. Page number 3 is not there in the main memory, so there will be a page fault interrupt. Following this page fault interrupt, again some page replacement has to be made because I don't have any free memory, any free frame at this moment. Now I have to find out that out of these pages in the main memory, which was brought first. Out of these pages, it is the page number 0 which was brought first. So page number 0 will be replaced by page number 3. So it will be 2, 3, 1. The next page, here you see the situation. The next page that is referred is again page number 0, and it is the page number 0 which has just been replaced. Naturally, it is an undesirable situation, but I don't have any option in case of it. In case of FIFO, okay. So again, following this page fault interrupt, I have to find out a page for replacement, and now the first phase out of these frames is frame number 1 to put in the main memory. So frame number 1 will be replaced. Situation will be 2, 3, 0. Okay. So next one that has been referred is page number 4. Again, page number 4 does not exist, so I have to replace one of the pages to make room for page number 4. And out of these pages, it is page number 2 which was brought first, so you replace page number 2 by page number 4. Okay. Again, the next page that is referred is page number 2, but 2 has just now been replaced. Again, I have the same situation. It is page number 3 which will be replaced by page number 2. So I have 4, 2, 0. The next one that has been referred is again page number 3. So you find that the 3 has just been replaced. I have to replace now page number 0 by page number 3. So 4 will remain, 2 will also remain, page number 0 has to be replaced by page number 3. Again, page number 0 is referred. So I have another page fault interrupt, and this time the page to be replaced is page number 4. So 4 is replaced by 0, this is 2, this is 3. Next time 3 is referred, which is there in the main memory, there will not be any page fault interrupt. Next time 2 is referred, that is also there in the main memory, there will not be any interrupt. Next time 1 is referred. Okay. So again there is a page fault interrupt, and I have to replace one of the pages. Now which page will be replaced now? Page number 2. So it will be 0, 1, 3. Okay. Next time again 2 is deferred. And now I have to replace page number 3 by page number 2. Okay. Next time 0 is deferred, there is no page fault, 0 is there. Next time 1 is deferred, there is no page fault because 1 is there in the main memory. Next time 7 is deferred. So again there will be a page fault. And which one has to be replaced now? Page number 0, which is to be replaced by 7. Other 2 pages will remain as it is. Okay. Next time again 0 is deferred. What is the page that is to be replaced now? Page number 1. So I'll have 7, 0, 2. Next time again 1 is deferred. So now page number 2 is to be replaced. So I have 7, 0, 1. And this will continue. Okay. So from this, I have to compute what is the efficiency of the system. And one of the measures of the efficiency is the number of hits. Hits means whenever a page is deferred and the page is found to exist in the main memory, that is called a hit. Whenever a page is deferred and the page does not exist in the main memory, that is called a miss. So I can compute 2 ratios. One is called the hit ratio or H, and other one is called the miss ratio or M. And hit ratio is defined as the number of hits that you have encountered out of the total number of accesses. In this case, the total number of accesses is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay? So the total number of page deference is 20, and the number of hits that you have is, here there was a hit because 0 was deferred, which was available in the main memory. Okay? Here, then here, I think only this, isn't it? So I have 1, 2, 3, 4, 5. Okay? So I have 5 hits. So hit ratio is 15 by 20. Okay? And naturally, the miss ratio will be 1 minus hit ratio. And, sorry, hit ratio is 5 by 20. And miss ratio is 15 by 20. Because there are total of 15 misses or 15 page fault interrupts out of these 20 page differences. And there are 5 hits out of the 20 page differences. Okay? So I can compute the hit ratio and miss ratio like this. Similarly, when I go for the other page replacement technique, I can also find out what is the corresponding hit ratio and what is the corresponding miss ratio. Okay. So if I come to the next technique, say least recently, if I go for the optimal technique, say I have optimal page replacement. So in case of optimal page replacement, what we have said is the page which will not be referred for the maximum period of time in future, that is the one to be replaced. Okay. But initially, I have initial 3 page faults because none of the frames, none of the pages are available in the main memory at that moment. Okay. So firstly, when this page 7 is referred, because page 7 does not exist in the main memory, there will be a page fault and 7 will be placed in the main memory. Then 0 is referred, again 0 will be placed in the main memory. Next, 1 is deferred, again 1 will be placed in the main memory. Okay. Next time 2 is referred. So there is a page fault interrupt. Now, out of this, you have to find out that which page will not be referred for maximum period. When 2 is referred, you find that next time 0 is going to be referred. Then the next one to be referred out of the pages which are available in the main memory is page number 1. Okay, so 0 is going to be referred next. After that, what is going to be referred is page number 1. It is page number 7 which will not be referred for maximum duration. Okay, so I will replace page number 7 by page number 2, and the situation will be like this: 2, 0, and 1. Next time, the page which is being referred is page number 0. So page number 0 is referred, which is there in the main memory. So there is no page fault interrupt. Next time page number 3 is referred, which is not present in the main memory, so there will be page fault interrupt. And following this page fault interrupt, the page for replacement that is to be selected is the page which will not be referred for maximum duration. So when this 3 is referred, you find that next time the page that is going to be referred is page number 0. The next frame that is going to be referred is page number 2. So I will not replace 2 and 0. Rather, I will replace page number 1. In case of FIFO algorithm, what we had done is we had replaced page number 0. Okay. So now what I will do is I will keep 2, I will keep 0, and I will replace 1 by 3. Okay. Next time 0 is referred, which is there in the main memory. Next time page number 4 is referred. Again there will be a page fault interrupt, and I have to select a page from 2, 0, and 3. So here you find that when 4 is referred, the next frame that is going to be referred is 3, page that is going to be referred is 2, next to that is 3. So I will keep 2 and 3, and I will replace the other one, that is page number 0. So the situation will be 2, 4, 3. Okay. The next page that is referred is 2, there is no page fault. Next one is 3, there is no page fault. Then 0, again there will be a page fault. And now the page that has to be replaced is 3 will be referred next, after that page number 2. Okay. It is page number 4 which is not going to be referred for maximum duration. Okay, so I will replace page number 4 by page number 0. So it will be 2, 0, 3. Okay. So next time 3 is referred, no page fault. 2 is referred, no page fault. Then 1 is referred, when again there is a page fault. And now the page that is to be replaced is which one? Page number 3. So it will be 2, 0, 1. Okay. Next time 2 is referred, no page fault. 0 is referred, no page fault. 1 is referred, no page fault. 7 is referred, again there is a page fault. So which page will be replaced now? Okay. Next time 0 is referred, 1 is referred. There is no page fault. So now you find that number of page faults that you have encountered using this optimal algorithm is 1, 2, 3, 4, 5, 6, 7, 8, 9. Whereas in case of FIFO method, the number of page faults was 15. Okay. So in this case, the miss ratio M will simply be 9 by 20, because there are 9 page faults, and the hit ratio will be 11 by 20. Okay. So you find that simply by changing your replacement algorithm from FIFO to optimal, the number of misses or the number of page fault interrupts has reduced drastically. However, the optimal algorithm assumes that you already know that what is the future requirement of pages by process, which you can never know. Because here always, whenever I replace a page, I am always looking in future. that whether that page is going to be referred next or not. But in general, it is not possible to know that future requirement of the pages for different processes. So the optimal algorithm gives you the best performance, but it is difficult to implement. Okay. So you'll see the other replacement algorithm.